I love it.
Just in case it wasn't clear.
That's so cute.
Costumes that we can read.
Can you actually see through those things?
They're just like career sunglasses.
Yeah, no, I see, but it looks hard to see through.
I'll be taking out process parts. Put it back over there,
Where is it? Go here?
What other thing? We should have a Ben Viddiddle first. Ben Viddiddle.
Ben Viddiddle.
Look like though. And what should be happening? For everyone, I'm Ben Viddiddle. Sure. I mean, I'm not, but you want to be?
Thank you so much.
You're welcome. Enjoy.
Maybe you mean it. Yeah, I know you do. Yeah, some B-roll.
You're welcome. Enjoy. All right. Happy Halloween, everybody. If you haven't seen the candy up here, please come help yourself or get some after class. And I hope you get to enjoy yourselves today. We'll see how the rain does. Anyhow, so today we are going to be discussing caches, which happens to be my favorite subject in computer architecture. Let's see how you guys like it. And so, excuse me, we're going to follow up on our discussion from Tuesday's lecture, where we learned about all the different types of memory technologies and how we can use them in a hierarchical fashion in order to take advantage of each of the trade-offs between these different technologies. And so what we saw last time was that the unfortunate, I guess, situation is that if you want to have a large memory, then you kind of have to deal with the fact that it's slow. Whereas if you want to have a fast memory, then you're going to have to deal with the fact that it's small and expensive. So what we, talked about at the end of Tuesday's lecture was that what we'd like to do is to see if we can somehow have the best of both worlds. And so how do we do that? The way that we do that is we use a hierarchy of memories. So we're going to use a small fast memory, and then followed by maybe some medium larger memory, and finally some very huge memory which is sufficient for all of our storage requirements. And as far as the processor is concerned, it's going to see it as if we have just one single memory here that's large and fast on the side. So what do I mean by that? What I mean by that is that as far as the programmers are concerned, the programming model is that you just have one large memory. You have one address space. You have no visibility into the fact that the way that this memory is implemented is actually as a hierarchy of memories. Okay, so the picture looks very simple, just like this. However, behind the scenes, what's happening is that the hardware is responsible for figuring out on its own which data should live in the different types of memory technologies. Okay, so what our memory actually looks like, and this is, you can have more levels than what I'm showing here, but essentially you have your CPU or your processor, which will talk to cache. The cache is going to be implemented in SRAM, which is our fastest memory technology after registers. And then, but because it's in SRAM, we can't have it be too large. And so then behind the cache is going to sit our main memory, which is going to be made of DRAM, or dynamic random access memory technology. And then behind that, we have some backup storage, which can be something like a hard disk, for example. Okay? So what we're going to focus on in today's lecture is the left side of this. And as I mentioned on Tuesday, we're going to be getting into talking about how we access the hard disk and memory that's off of the chip in next week's lecture. Okay, so this is the part that we want to focus on now. So what we're going to do is we're basically going to have a cache that's going to sit between our CPU and our main memory. And you might actually have multiple levels of caches if, we deem that appropriate for whatever processor it is that we're building. But for simplicity, let's just assume we have one cache and then a main memory. So what does this cache do? This cache is a small and very fast memory, which is going to store basically locations that hopefully we need to access again in the near future. So what does that look like? Suppose that I have, an address that the CPU is asking for. The first thing it's going to do is it's going to check, is that location in my cache? If it is, I'm going to get the data back very quickly. If it's not, then I'm going to go and I'm going to check in my main memory, is it located there? And I'll get it back from there, give it back to the processor, and also give it back to my cache. Okay, now why do I also want to put it in my cache? I want to put it in my cache because it turns out that if I'm currently accessing something from main memory, it's very likely that I'm going to want to access it again in the near future. So even though this time I wasn't able to find it in my cache, if I bring it from main memory into my cache when I went ahead and fetched it for the CPU, then I'll have it for the next time that this address is requested. And so when I request something from the cache, I said two things can happen, right? Either we have a cache hit, which gives the data back very quickly, or I have a cache miss, in which case I go and I fetch the data from memory, and I also bring it back into my cache. And so we concluded saying that the processor thus needs to be able to handle variable response times from the memory, right? Because if it gets it from the cache, it's going to be very fast. If it gets it from main memory, it's going to be a lot slower. All right. So the first few slides here are just a review, so I'm going to go through them relatively quickly. So then we talked about, why is it that caches work? Well, the reason that caches work is because we're basically able to predict, essentially, which requests are going to be made based on which requests we've seen in the recent past. Okay? And the reason that is because we have what's called locality in our programs. We have, both in our programs and in our data accesses, we have two types of locality. The first is temporal locality, which is what I just mentioned, which is if I am accessing address X right now, I'm very likely to access address X again in the near future, right? So why does that happen? Well, when I run loops, I execute my instructions numerous times. When I access variables on my stack, I'm potentially going to be accessing the same piece of data multiple times, and so on. Okay, so that's temporal locality. The second type of locality is spatial locality. And what spatial locality says is if I'm accessing address X at any point in time, then I'm very likely to access an address that's near X, like X plus 4, in the very near future, right? And so that one's pretty easy to see, right? If our code, for the most part, is sequential, right? So if I'm accessing an instruction at address 0x100, most of the time my next instruction is going to come from 0x104. Okay? Similarly, if I'm accessing an array of data elements, those array elements are stored in contiguous locations in memory. And so that means that if I'm accessing, array element 0 from location 0x200, then array element 1 is going to be in location 0x204. Okay? And so because of these two reasons, caches end up producing a high hit rate, meaning that by using this fact, we're able to make it likely that the next time that we want to access this piece of data, it's actually going to be in the cache, and so we're going to get a hit. And so the result is that what we really care about is our average memory access time. Okay, so let's go over how we compute the average memory access time. Well, as we said, we're always going to first check our cache to see if the data that we're looking for is there. Okay, so in order to check our cache, it takes us hit time, which just basically corresponds to the time to look up something in the cache. Okay, now if we don't find it in our cache, which is going to happen misratio fraction of the time, then what's going to happen is that I have to go and fetch it from main memory. And so I have to pay what's called a miss penalty, which is the amount of time it then takes me to go and fetch from main memory after I check the cache. Okay? So on a miss, I'm paying both the hit time and the miss penalty, whereas on a hit, I only pay for the hit time. Any questions about that? And of course, we saw last time that you can also apply this equation recursively if you have a hierarchy of memories. All right, so we're almost on to the new material, and so this is where we ended last time, which is we said that we've got our processor, we've got our main memory, and in the middle sits this cache. Now the cache is small, so it's not able to store every single piece of data that's in our main memory. And so in order to know what a particular piece of data, where it comes from, not only do we need to store the data in our cache, we also need to store the address of where that data came from in the cache. And that's what's shown here in this tag field. Okay, so the tag basically tells you what's the address that this line in my cache is storing, and then the data field has the actual contents of the memory at that address. Okay, so if I'm trying to fetch address X, what's going to happen? I'm going to check all of my tags, and I'm going to say, is one of my tags equal to X? If it is, that means I got a hit. I found my address X in my cache, and so all I need to do is return the data that's in that same line. Suppose, for example, that X was equal to A, so I would just return memory of A back to my CPU. Okay? But if I don't find a match in any of the tags, then what happens is that I get a miss. Okay, so what happens now? If I get a miss, this means that I didn't find it in my cache, so I have to now go to main memory and fetch the data from there. And so I'm going to go ahead to main memory, I'm going to read that address X, I'm going to get the data back and send it back to my CPU, but in addition, I'm going to put it into my cache. So what does it mean to put it into my cache? Well, generally, after we've been running for a little while, our caches are always full, okay? Because we want to be using them, and so we're filling them up. And so in order to bring something into my cache, I have to take something out of my cache, okay? So on a miss, not only am I fetching something from main memory, I'm also deciding which line in my cache I'm going to take out so that I can bring this new line that I just fetched from main memory into my cache, okay? And we're going to see a lot of detail about that in today's lecture. So you might be asking yourself the following question. If you recall on Tuesday's lecture, we saw a slide on multi-ported SRAMs, and we saw that basically the area grows as n squared with the number of ports that this SRAM has. And so it's very expensive to have multiple ports connected to this SRAM. So what does that mean? What really happens is that we have single-ported SRAMs. And so what that means is I can only look at one value at a time in my SRAM. So when I'm trying to see if my address X is present in any of the cache locations, I can't check all of them at the same time, right? So you can imagine that, if I first have to check, the first row, and then I have to check the second row, and et cetera, even though this cache is pretty small, that's going to take, a not insignificant amount of time, right? And so that's not really good enough for us. And so what we're going to look at today is, well, how could we use a particular algorithm to determine where in the cache we should be looking for this address X so that we can reduce that search time? Okay? All right. So this brings us to the first and the most basic type of cache, which you should have seen in yesterday's recitation, but we're going to go over it again today. And so this is called a direct mapped cache. So how does a direct mapped cache work? The idea is that given a particular address, there's exactly one cache line that address can map to. Okay, so how does that work? Well, if I look at this 32-bit address, which is the address of the memory location that I'm trying to access, I can divide up that address into a number of fields. So first of all, the bottom 2 bits are always going to be 0, 0. Why is that? Can anybody tell me? Yeah.
The memory addresses are multiple to 4 up to the last 2.
Exactly. Our addresses are in bytes, but we're always accessing 32-bit values, so we're accessing them in word boundaries, and so the bottom 2 bits are always going to be 0. Okay, so we can ignore those bottom 2 bits. Now, the next set of bits are what we call the index bits. So in this example, I have an 8-line cache. In order to select one of 8 lines, I need 3 bits. And so I'm going to have the next 3 bits of my address be used for my index. And so it's going to select exactly 1 line of my cache. And so in this particular example, the index happens to be equal to 2. And so that means that this particular address could only be found in index 2 of my cache. Okay, so that's the only place where I need to search and compare the tag. I don't have to search in every single line of my cache. Okay, and so by doing this, I make my search much, much faster. Okay, all right, so now what data has to go into my actual cache? Well, we mentioned that we have the data that we're storing, and in addition, we have some information about the address that data corresponds to, and we call that the tag. And we'll if you look here, you'll notice that this tag is just 27 bits and not 32 bits, even though our addresses are all 32 bits. So who can tell me why this tag is just 27 bits? Yeah. Exactly. If I know which line in my cache I'm looking at, I can reconstruct those bottom 5 bits of my address. So all I need to actually store in my tag field are the top 27 bits of my address. Okay, so when I go to check if something is in my cache, what I'm doing is I'm comparing my tag, which is the remaining bits after my index bits, of the of the address that I'm looking for, and I see whether it matches the tag in the line of the cache that I'm looking at. Now, if I get a match, then the next thing that I check is whether the data in this line is actually valid. Why would I need to, why wouldn't my data always be valid in my cache? Any ideas? What happens on startup? I might have garbage in my cache, right? So on startup, I need to make sure that all my valid bits are set to 0. And so I don't mistakenly think that I have a piece of data that I haven't actually brought into my cache yet. Okay? Because remember that SRAM does not actually store things when power is off. So if I powered this thing down and I bring it back up, it's going to have potentially some garbage data in there. Okay? So in addition to having a match on my tag, I also need to check that my valid bit is 1. And if both of those things are true, then I got a hit, and so I simply go ahead and return the data that was in that index of my cache. Okay? So now let's go through an example to make sure it's clear to us how these direct mapped caches work. So in this example, we're going to have a cache that has 64 lines in it. And so in order to access 64 lines, I need 6 index bits. All right, and the particular address that I'm going to try to fetch from memory is 0x400C. Okay, so what's the first thing that I need to do in order to check whether this thing is in my cache? First thing I'm going to do is I'm going to translate that address to binary, and I'm going to split it up into the various fields that we talked about. Okay, so the bottom 2 bits are always 0. My index bits are the next 6 bits of my address, and so in this case my index is 3. And the rest of the bits, the higher order bits, are my tag. Okay? So now what do I do? Well, now that I know that my index is 3, I'm going to come here into my cache and I'm going to look at index 3 and I'm going to check whether the tag that's stored at index 3 is equal to the tag that I'm looking for. And is it? In this case? What am I looking for? I'm looking for a tag of 0x40. I have a tag of 0x40, and my valid bit is 1, so I got a hit. Okay? So what's the data that I return? Now remember, the data that I'm returning is not the address. It's not this 0x40. It's the data that's stored on that same line. So what I'm returning from this read or load operation is this 0x42424242. Everyone comfortable with that? Good. So now, let's suppose that instead I asked you, to access address 4008. And I want to know, is that going to give me a hit or a miss? Can anybody tell me? What's going to be the difference in the index of an address that was 400C versus 4008? The only thing that's going to be different is that this bit here is, this one is going to be a 0 instead of a 1. Okay, so what does that mean my index is? My index here is a 2. If I go and I look at index 2 in my cache, I see that the tag is 0x58, whereas the tag I'm looking for is, again, 0x40, and so this time I got a miss. All right? So that's basically how we go about looking up something in our cache. All right, and this just summarizes the fact that we don't actually need our tag to be 32 bits wide. It's 32 bits minus the number of index bits minus those 2 bits of the byte offset. Okay, so now let me ask you a question. You all might have, happily accepted which bits I happen to say were the index bits, but can we actually think about it a little bit? Can anyone tell me why I chose these low order bits to be my index bits rather than, let's say, the top of my address? there a reason for that? Yep.
For spatial locality, a lot of like the same addresses are going to be sort of in the same lower bits.
In the same upper bits. Right? So in other words, if I wanted to access, let's say, address 100 and 104, the top bits of both of those are 0. And so that would mean that both of those locations would map to the same location in my cache, which isn't what I want, right? I want these locations that I'm likely to want to access both of them to both be able to fit in my cache. So if I use the lower order bits, then what happens is that address 100 and address 104 are going to map to different indices. Okay? And so this helps us take advantage of the locality that's in our cache, and it does two things. It allows consecutive memory locations to be able to be in the cache at the same time, and it also reduces the likelihood that I'm going to just take something out of my cache because I happen to have something else that mapped to the same location. So so the next thing that we want to talk about is, well, if we want to continue thinking about this line of how do we take advantage of locality, we can actually go a step further beyond, where we selected our index bits to be. So far we've been talking about every time that I bring something into my cache, it's one word wide. But if spatial locality, is something that we know exists, then instead of just fetching, one word from memory whenever I get a miss, it might be useful to fetch a few words from memory, right? Because suppose that, I try to fetch address 0x100 and I got a miss. Well, if I at the same time as I bring 0x100 from my main memory, I also bring 0x104, 108, and 10C, then if I happen to now go and request address 104 or 108, whatever, then when I request those other addresses, which I'm likely to request because of spatial locality, I'm going to get a hit. Okay? And so the way that we describe this is as a block size. Okay? So this refers to the size of the data field. So how many words do we store at a particular index in our cache? All right? So this is going to help us in a few ways. Number one, it helps with spatial locality because it doesn't cost us n times as much to bring n words from memory that are next to each other as it does to bring one. And we'll see actually a graph of what that actually looks like in a second. In addition, the other advantage is that if you look at the amount of memory that's dedicated to the tag field. Remember, our memory is very precious to us. We want to be able to store as much data as possible in it. And so before, my tag field was almost as large as my data field if I had, one tag for every one word of data. But now I have, a tag field that's, on the order of one of these 4 words. And so now I've gone from a ratio of 50% of my data being used for the tag to being 20%. Okay, so clearly this is a much more efficient way of storing the data, assuming that I am actually going to need, on most occasions, all of those words in that block. All right, so how do we go about accessing something that has multiple words in the block? So in this example, we have 4 blocks, meaning we have these 4 lines, and each of them is of width 4. And so I have a total of 16 words in this direct mapped cache. So once again, the bottom 2 bits are always going to be 0. In this case, the next 2 bits are going to be used as a block offset. Okay, so they're going to pick one of these 4 words in the case that I get a hit in my match in my tag and my valid bit. And then the next set of bits are my index bits, which work just like before in that they select one of the lines in my cache. And so then I'm going to compare the tag of the line that was selected by the index bits. If I get a match, then I'm going to go ahead and pick the word that comes from the line that was selected. Okay? So let's talk a little bit about how far we can take this. Okay? So it does make sense that larger blocks are going to help us, but how large should they be? Okay, well, as we start to make our block size larger, we're going to be able to take advantage of spatial locality, as we mentioned. But every time we fetch, 4 pieces of data instead of 1, it does cost a little bit more than fetching just 1 piece of data, and so my miss penalty is going up. In addition, depending on how I make use of this and how big I make my blocks, if the total number of words in my cache is fixed, then by making, the number of words in my block larger, I'm making the number of lines in my cache smaller. And so I might start to have more misses because the number of lines is smaller. And so this is what the trade-off looks like. So as my block size gets bigger, first of all, for my first word, there's this large overhead that I pay. And then it is the case that as I bring more words in, it costs me a little bit more, but you see that it's just an incremental amount of over the first block. Okay? And so this is the miss penalty, which corresponds to the amount of time it takes me to fetch that number of words from main memory. What about my miss ratio? Well, as we said, initially, as I'm increasing my block size, I'm reducing my miss ratio because I'm taking advantage of spatial locality. Okay? But if I make my block size too large, then what's going to end up happening is that I don't have enough lines in my cache, and so I'm ultimately going to pay the price in temporal locality, and my miss ratio is going to start to go back up. And so if I put both of these together and look at the metric that I actually care about, which is the average memory access time, then I see that, there is some minimum AMAT there's some block size which is going to produce a minimum AMAT, which typically happens around 64 bytes or 16 words. Okay, so a block size of 16 words. All right, so next thing that I want to think about is, well, what kinds of things cause misses in my cache? Okay, and so we're going to look at this by looking at this example. For this particular example, what we've got here is, assume that you have a little piece of code that's 3 lines long, and this piece of code is accessing 3 data elements, and you're told that that your code begins at address 1024 and the data is at address 37. And now, just to avoid having to deal with these 2 extra bits, these are going to be word addresses, not byte addresses. Okay, so assume that I've already thrown away those bottom 2 bits. Okay, so word address 1024 is going to map to index 0 of my cache. Okay, then I go and I fetch my first piece of data, which is at word address 37, and so that maps to address 37 in my cache, and so good, they map to different locations. And if I look at the entire thing here, and this is a loop that I'm executing repeatedly, after I've brought these data elements into my cache the first time, every time afterwards when I try to access these locations, I'm going to get a hit because they're not conflicting with each other. Okay, so my instructions are going to go at indices 0, 1, and 2, and my data is going to go at indices 37, 38, and 39, and so all of the data and all of my loop instructions can live in my cache at the same time. Okay, but now, suppose I'm running the exact same piece of code, but my data just happens to be located somewhere else. This is could potentially drastically change the performance of my cache, right? Suppose that instead my data was at address 2048. So now, if I look at the indices that the instructions and the data map to, well, the instructions still map to the same indices, 0, 1, and 2. But now, my data happens to also map to 0, 1, and 2. So what happens now? Now, every single one of my memory accesses, both my instruction fetches and my data fetches, are going to be misses. Okay? This is what's known as conflict misses. Okay? This occurs when too many things are potentially being mapped to the same index in our cache. Okay? And so this is something that we definitely want to be cognizant of, that we have to be careful to not have too many conflict misses. And what we notice is, well, you know, in this example, it's really not so great that the behavior of my program can be so different just based on where my data happens to be located. Okay? So what I'd like to have my cache do is not be, you know, so rigid in terms of saying, well, for any given address, there's exactly one location it can come from. Instead, let's give it some flexibility. So how do we do that? The other extreme from a direct map cache is a fully associative cache. So what does a fully associative cache mean? It means that I'm not using any index bits. So my data can go into any of my cache lines. And what does that mean? That means that I actually have essentially one port per cache line, and I have one comparator per cache line. Okay, so this is very expensive to build, right? I'm looking at all of these tags at the same time in a fully associative cache, so that the amount of time that I spend searching the cache for the address I'm looking for is still low. Okay? So let's just see, you know, how does the search in a fully associative cache work? It looks pretty similar, you know, to our direct mapped cache, in that the bottom two bits are 0, 0, and we just ignore them. The next set of bits are our block offset bits, and so if I have a block size of 4 words, then I'm going to have 2 bits that select one of the words in my block. And finally, the remaining bits are going to be tag bits, because in a fully associative cache, I don't have any index bits, right? Because every address can go in any of the lines of the cache. Okay? Any questions about fully associative caches? Okay. And so then, of course, we have some middle ground, which is what's called an n-way set associative cache. So this is somewhere in between, where what we have is we basically have n direct mapped caches operating in parallel, okay? And so what happens now is, for any particular address, it can go in one of n locations, or one of n ways is the terminology that we use in associative caches, okay? And so basically the index is going to map to what we call a set. And so these index bits that we have, instead of just selecting one location in my cache, it's going to select one of 4 locations, or one of n-way locations in my cache, okay? And so now I have a little bit of flexibility. So if I go to that program that we were just looking at, where both my instruction and data mapped to the same indices, in this case, they're not going to miss, because I could have my instructions live in one way of my cache, and I could have my data live in another way of my cache, and even though both of them map to the same indices, they're not going to conflict with each other. Any questions about that? Okay. So basically, the way that I would search a n-way set associative cache is I first have again, my bottom 2 bits are my 0, 0. My next set of bits are going to select my block from the word within my block. The next set of bits are the index bits, which select the row, essentially, of my cache. And finally, the remaining bits are the tag. And so now, when I do my comparison, I'm going to compare my tag to the tag of each one of these ways for that set to see if any of them match. And if any of them match, then I'm going to return the data from that way that matched. Okay? All right, and you can kind of think of a fully associative cache as an extreme case of this, where the number of ways is basically equal to the number of lines in your cache. All right, so we're almost there. You know, we now figured out how we can design our cache in 3 different ways and what the trade-offs are between them. But there's still a few more things we have to deal with. So in this simple case of the direct mapped cache, there was exactly 1 line that our particular address could map to. Okay? But now that we've introduced n-way set associative and fully associative caches, for an n-way set associative, there's one of n locations that any address can go to. And for a fully associative, it can go to any of the cache lines. So what this leads to is the fact that we have to think about what's our replacement policy. So when I need to fetch something from main memory because I had a miss, and I need to take something out of my cache, in a direct mapped case, it's clear which one I'm taking out of the cache. I'm just taking the one at the index that I need to put the new piece of data in. But when I have associativity in n-way set associative or fully associative, I now have choices about which word I'm going to take out of my cache. Okay? So, what are my choices? Well, ideally, what I want to do is I want to get rid of the word that I'm going to want to access the furthest in the future. Okay, but clearly I can't, tell what the future is. So what we're going to do is we're going to try to predict the future by looking at our past behavior. Okay, and so essentially, because of locality, we can reason that something that I've accessed recently, I'm likely to access in the near future. And so the thing that we would like to get rid of is what we call the least recently used piece of data in our set. Okay? Now, to actually compute an exact least recently used out of n values can get kind of expensive. So often we do an approximation of this. But in a small associativity, you could even potentially, keep the exact list of all of the permutations of the n accesses per line. All right, so what are some alternatives to least recently used? So least recently used is the most common, and you're going to be seeing this in a lot of the exercises you do. But there are other potential policies like first in, first out, or even random. Neither one of these is used very much, but it's good to understand that in the case of using least recently used, there are some sequences of addresses that are going to make any cache that I give you behave poorly. Whereas if I use, for example, a random replacement policy, then I'm not going to be, there's not going to be any kind of sequence of addresses that's just always going to do poorly on my cache. And if we have time for that, we'll get to an example at the end. Okay, so the last thing that I have to answer is how do I do writes? So until now, everything we've been talking about is basically reading from my cache, right? I've been just trying to load data from memory. Okay, but we also have to be able to store things to memory. Okay, so when I store things to memory, now that I have a cache between my memory and my CPU, I have some choices to make. When I do a store into a particular memory location, I can either require that my cache and my main memory remain consistent with each other. If I require that, then I'm using what's called a write-through policy. So every time I write something to my cache, right, so I search for a particular address in my cache, it's there. I now want to update that value. So not only do I update it in my cache, but I also go and I write the updated value to main memory. Okay? This turns out, to be very expensive, because think about it. I might have a reason to store multiple values into the same location and only care about that last value. So why should I pay this bandwidth price of writing the value back to main memory, every single time, when all I really care about is the final value? Okay? So the alternative to a write-through policy is a write-back policy. So what does write back do? Write back says, well, I'm just going to write to my cache, and I'm not going to worry about the fact that my main memory and my cache get out of sync. But if I need to replace a line, meaning I need to take it out of my cache, that's when I'm going to go and I'm going to write it back to main memory. Okay? And there's also some hybrids of these, but basically the most commonly used is this write-back mechanism. And so we're going to take a look at, an example of how this works. So let's take a look at both a write-hit situation and a write-miss situation. And so let's assume we have this 16-line direct mapped cache with a block size of 4. So I have 4 words per line of my cache. And now I'm trying, and the write policy is the write back policy. And I'm trying to write the value 9 to this address 4818. Okay? So let's see how I go about doing this. So I'm going to start off by translating my hexadecimal address into binary and dividing it up into these various fields. And so what I have for my fields are the byte offset, as expected, is just 0. The block offset is 2. My index is 1. And my tag is 0x48. All right? So now I can come here into my cache at index 1, and I take a look at the tag that's stored there. And the tag is 0x48, which matches the tag that I'm looking for. So I get a hit. Okay? So now I'm still not done. What do I have left to do? I'm doing a store operation, so I need to update that memory location or that cache location. Okay, so I now use my block offset bits to identify exactly which of the words within my line is the one that I'm actually trying to modify. The block offset is 2, and so that means that this is the location that I'm actually writing to. And so I go ahead and I update that to be a 9. And in addition, I update this additional field that I need to add to my cache, which is called the dirty bit. Okay, so what does this dirty bit tell me? This dirty bit tells me that I've done a write to that line of the cache. So upon replacement, if the dirty bit is equal to 1, then what that means is that I'm going to have to write that line back into main memory before I can bring my new line from main memory. Okay? On the other hand, if the dirty bit is 0, that means that all I've done are reads from this line. So I haven't modified the line at all. And so it's still exactly the same as what's in my main memory. And so there's no need to write it back. Okay? So now let's take a look at a write-miss. All right? So again, we're trying to access the same location, but this time when we go and look at our tag, we have a mismatch. Okay, so I have a miss. So what happens on a write-miss? And this is important. This is something students often get confused on. So remember, the block size of 4 means that anytime I'm fetching something from main memory, I'm going to bring 4 words in at a time, and I'm replacing the 4 words or the full line of the cache at the same time. So when I get this miss on this 0x280 tag, what's going to happen is the first thing I need to do is I need to look at the dirty bit of that line. In this case, it happens to be a 1. So I have to take this entire line and write it back to main memory at the addresses that correspond to a tag of 280. Okay, which happens to be, and a tag of 280 and an index of 1, and so those happen to be addresses 28010 through 28010C. Okay, once I've written it back to main memory, then it's fair game to evict it from my cache, and so now I can bring the data that I'm actually looking for into my cache. So I go ahead and I replace that entire line, okay? And so notice now, my tag is 48, and so this data, even though I'm only trying to access one of these 4 words, I'm actually first updating all 4 of them, okay? Because all 4 of them have to agree with the tag that corresponds to that line. So now that I have, the correct tag in my cache, now I can go ahead and do a store at the block offset of 2, and so now I'm going to replace this 3 with the 9, and I'm going to set my dirty bit to 1, so when this line gets replaced, I'll know that I did a store to it and it needs to be written back to main memory. Questions? Good. Hopefully that means I did a good job explaining. All right, so I wasn't sure if we were going to have time to, so this is just a summary of basically the different kinds of trade-offs that you're going to have to consider when you do cache design. But with the last couple minutes, I just want to show you a quick example, which is just meant to illustrate that regardless of which cache configuration you have, I can always give you some kind of memory access sequence that's going to make that cache not have a good performance, okay? So what we're going to do here is we're going to quickly compare 3 caches. We have a direct mapped cache that has 8 locations in it, and the block size is size 1. And we have a 2-way set associative cache that also has 8 locations in it, but we only have a total of 4 indices because it's a 2-way set associative cache. And finally, we have our fully associative cache that has 8 locations, so the data can go into any of those 8 locations. And what I'm going to do is I'm going to run through this sequence of memory accesses. Okay, so I'm accessing address 0, then 10, then 0x4, and then 0x24. And I want to see what the behavior is going to look like on these different caches. Okay, so we're going to do this quickly because we're basically out of time, but you can go through these on your own as well. But so basically what happens is I'm going to take a look at the address I'm trying to fetch, and I'm going to figure out for each of the cases which index it goes to, except for the fully associative where it can go anywhere. And so I find that address 0 goes into index 0, both in the direct map, the 2-way, and in the fully associative it can go anywhere, so I'm just going to put it here. Okay, I do the same thing for the rest of the addresses, and I find that 10 goes in index 4 of my direct map cache, it goes in index 0 of my 2-way set associative, but now, because I have 2 ways, I don't have to get rid of the 0, even though they both map to the 0 index. Okay? And then in my fully associative, again, I can just choose another location. And if we fill in the rest of these values, what we find is that when we get back to address 0x24, the index happens to be the same as the index of the 0x4 address for the direct mapped cache. Okay? So what that means is that in the case of the direct mapped cache, as I loop back through these instructions, the 0x4 and 0x24 address are always going to miss, And so that means that I have the following hit rate. On my direct mapped cache, I have a 50% hit rate, whereas in my two-way set associative cache, I have a 100% hit rate, and in my fully associative cache, I have a 100% hit rate as well. And so I'll let you guys go through the next two examples, but basically I'll just say that the next sequence shows you a situation where the where the direct mapped cache is the one that does the best. And the last situation shows you a situation where the two-way set associative does the best, okay? So if you go through in detail, you can see that even though I didn't change the configuration of my caches, there is no way to say, oh, this configuration is always better than some other one, okay? So that's it for today. Happy Halloween. Come grab some more candy, and we'll see you next week.